This one is a classic Atwood machine problem here. We've got our frictionless massless pulley here, 4 kilograms on this side, and a total of 3 kilograms on this side. They're just trying to throw you off a little bit by putting them separate. So anyone would probably guess here that that means that this thing is going to accelerate this way. So the 4 kilograms is going to come down and the 3 kilograms on this side are going to go up. So it is going to start to rotate clockwise there. They didn't ask for a free body diagram, but I'm going to go ahead and throw it in here real quick. There is a force of gravity, I'll call it on the 4 kilogram there. So that is down there. There is a force of gravity on the 2 kilogram. And if they asked for it, how would it compare relative to this? Well, it's about half the size. So it's hard to see there, but it says force of gravity on 2. And then there would be one more here. This one would be half the size of that. We can call this the force of gravity on 1. Each one of these also has a tension point on it. So on the 4 kilogram, we have a tension up this way. I know that that tension is less than this force of gravity because it's going to accelerate downwards. I know that that tension is actually, because the tension is the same everywhere, is the same as this tension over here, and that this tension has to be bigger than that force of gravity because this one's going to accelerate upwards. Now, what's a little bit different than the one we did in class here is that this one has its own tension. I'll call this T1 there because it's acting on the 1 kilogram, and it's got to be bigger than that one because that 1 kilogram is going to accelerate upwards. So let's actually find the acceleration of the 4 kilogram block here. Now they say they want the acceleration of the 4 kilogram block, but everything in the system is going to accelerate the same. So I am actually going to find the acceleration of the system here. So in order to do that, let's set up our Newton's second law. The sum of the forces on the system is equal to the mass of the system times the acceleration of the system. And that acceleration of the system, again, will be the acceleration of block 4. So what forces do we have? Don't count any of the tensions because those are internal forces. So we have the force of gravity on 4 one way. I'll call that direction it's going to move the positive way. We have the force of gravity back on the 2 block the other way, and we have the force of gravity back on the 1 kilogram block back that other way as well. The mass of the system will be all 3 masses added up together. So I'm going to go ahead, 4 plus 2 plus 1 is 7 kilograms, and we can solve for this acceleration of the system. These are pretty easy to find. Each of these are going to just be mass times gravity. So we have 40 newtons down on the 4 kilogram block. We've got 20 newtons back the other way on the 2 kilogram block, and we've got 10 newtons back the other way on the 1 kilogram block. So now that we go to solve here, we can see on this side we're going to get a total of 10 newtons, left over in the end. So 40 minus 20 minus 10 is equal to 7 kilograms times the acceleration of the system. So the acceleration of the system will be 10 newtons over 7 kilograms. And so that will work out to be 1.4, let's just call it. So 1.4 meters per second squared. That's the acceleration of the system. That's the acceleration of block 4. That's the acceleration of block 2. That's the acceleration of block 1. Everything in the system accelerates the same. So now on this first one up here, it says what is the tension in the string supporting the 4 kilogram block. So I'm going to come back and for a moment here look at this part of the picture right here and use that to create a equation on this side here. So when we go to set this up, I'm going to say that the sum of the forces, the sum, let me try again, of the forces on block 4, was what I was trying to write there, is going to be equal to the mass of block 4 times the acceleration of block 4. Well, what are the forces on block 4? Again, I'm going to call the way that it moves positive, so I'm going to call this one positive. So we've got the force of gravity on block 4 down, and we've got the tension back up the other way. So that will be the mass of 4 times the acceleration of 4. I'm going to do 2 things at once now. I'm going to move the tension over here, and I'm going to move this over to this right side over to the left side. So I get tension is equal to the force of gravity on 4 minus the mass of 4 times the acceleration of 4. I'm going to substitute in here what you would get. Generically, in case this didn't have numbers, it's going to be the mass of 4 times gravity minus the mass of 4 times the acceleration of 4. And this, again, gets you to, if you factor out the mass, this gets you to what we were calling in class, or I was calling, and the rest of the world should call too, the Frankenhoff equation. So now we can plug in here and solve. The tension is equal to the mass of 4, which is 4 kilograms, multiplied by gravity, which is 10 meters per second squared, minus the acceleration. And we solve for this over here. Remember, it is 1.4 meters per second squared. So this will be 1.4 meters per second squared. And then you take 10 minus 1.4 times 4, and you get 34.4. So the tension is 34.4 newtons. Notice that that's less than 40 newtons. If you just held that block there and kept it from moving at all, then the tension would have to be equal to its weight, which would be 40 newtons. But you can see that this tension should be less because it's not just moving downwards, it's accelerating downwards. So your force upward must be losing to the force downward, so the tension must be less than its weight. Here, this is basically the exact same thing. We could set it up again. You could use all of this that we just did here and solve it for the tension for mass 1. And you don't even have to change anything here. So the tension in the string for mass 1 follows the same formula there. And so we can plug in there, mass 1 is 1 kilogram, and you get gravity, again, is 10 meters per second squared, and the acceleration is 1.4 meters per second squared. So then you get 8.6 newtons. Oh, nope, sorry. Let's redo that one. Here. I made a mistake on that last one there for a second. The reason that it's not the same is on the 1 kilogram block here, the tension is up, and I'm calling the way that it moves positive, and the force of gravity is down. What difference does that make? Well, when you go to set it up, the sum of the forces on block 1 is equal to the mass of 1 times the acceleration of 1. We've got tension up is winning, minus the force of gravity down, which is losing, is equal to mass of 1 times acceleration of 1. So now, when I go to solve for the tension, here's the difference here that I just made a mistake on, is it's the force of gravity plus the acceleration. So when we go to solve for it, now we get the mass of 1 times gravity plus the mass of 1 times acceleration. On the case of 4, those two values were minusing each other. So now we can substitute in here, we get 1 kilogram times 10 meters per second squared plus 1 kilogram times 1.4 is our acceleration of our system. So that means all together we get a tension of, this will give you 10, this will give you 1.4, so 11.4 newtons is the tension on block 1. I do want to mention sort of thinking how I just caught my own mistake here and how you can use it to catch your own mistake when doing a problem maybe on the test. This thing's accelerating upwards. So I know that its tension is winning. So I know that tension has to be greater than the force of gravity. So for a moment there on this, I wasn't thinking until I got that the answer had to be 8.6. And then I just realized they were like, wait, that's a mistake. That can't be right. Because if it has a mass of 1 kilogram, it has to weigh 10 newtons. So, and since it is moving upwards, the tension has to be bigger than the force of gravity, and the tension has to be greater than 10 newtons. And so this is the answer. But it is good to sort of learn thinking ahead of what the answers have to be so you can catch a mistake like I just did before you just send it off to the College Board.